recording while we're thinking about it. Can I get a mic check? 1, 2.
1, 2, 1, 2, 3.
All right, hell yeah, we're recording. So, I'm gonna keep it a $1.50. I don't totally understand why this class's material specifically isn't just grouped in with tomorrow's class's material as well. I don't understand why he separates motional EMF and Faraday's/Lenz's law. Because honestly, the motional EMF is literally just a derivation of Faraday's law, right? I get mixed up. Lenz's law is the one where you figure out the direction. Faraday's law is the yeah. Anyway, honestly, emotional EMF isn't really all that complicated. It's pretty much, you'll see one of two examples for your questions on emotional EMF tomorrow. And that's pretty much it. And it's just getting comfortable practicing and understanding it. Like most things with physics.
That's the one I was trying to figure out.
So
it took a while to even figure out the graph on that.
Yeah.
Ugh.
So let me ask you, what exactly is motional EMF?
Give me a second to pull up my notes. I was doing all kinds of stuff before this, so I didn't get enough time to pull up stuff.
Like sleeping?
Well, no, I actually was doing chores with that. I mean, yes, I slept in late, don't get me wrong. That is the true thing that did happen. I just still had other things, like helping taking out the dog and all that.
Mm-hmm.
So an emotional EMF.
An emotional EMF?
Oh wait, didn't you? Is that the question you asked? Or
Yeah. Yeah. So what is motional EMF?
I'm honestly trying to remember how to even say it. It's supposed to be how there's movement, of course. It's how an object moves within the magnetic field, I believe, with the charges and everything inside it.
And what specifically happens with that movement in the magnetic field? What happens because of it?
A charged particle goes to one side. A positive charged particle goes to one side, and the other charged particle goes to the other side, trying to hit equilibrium while it's moving.
Mm-hmm. And so basically, what you're saying is, if we have a bunch of, we have an area of magnetic field, and then we have a bunch of positive and negative charges enter it. Let's say the magnetic field is out of the page, and a group, some arbitrary shape of positive and negative charges enters the magnetic field. What's going to end up happening?
They're going to try to go to one side. The positives trying to go to one side. The negatives go to the other.
So which side is which? How's it going down?
It depends on the movement of the object and also the magnetic field.
So the magnetic field is, let's say, out of the page, and the object is moving to the right here. What's going to end up happening?
The positive charges should be going to the bottom. If I'm right on that right-hand rule, see, to the right. Yeah, should be going to the bottom of the object, the positives.
Exactly. So let's say our object is in the magnetic field. All the positive charges are going to want to end up moving to the bottom, because right-hand rule, point your fingers to the right, point your palm out of the page, your thumb is pointing down. What about the negative charges?
To the top.
Exactly. Exact opposite direction. So we have all these positive and negative charges that end up being pushed to opposite sides of whatever it is that is traveling through the magnetic field.
And I believe the electric field's actually going from positive to negative.
So we have some sort of an electric field in here.
I believe so.
Mm-hmm. And what else is caused here? What else is created here? I mean, the electric field, and then also
the force of the electric field.
oh, I mean that's like that would I would include that with the electric field.
Okay, then. Well, honestly, I don't know what else is.
Is it the potential difference?
Exactly. We create a potential difference. It's like, imagine capacitor plates. I mean, essentially, we've sort of created a positive plate on the bottom and a negative plate on top. And obviously, there's an electric field between them and also a potential difference. What happens with potential difference? Wording. So is this going to be, which side here is going to have the higher potential difference and which side is going to have the lower potential difference?
It's going to be the side inside the magnetic field.
Well, the whole thing is inside the magnetic field.
Oh.
This is just an arbitrary, blob of charges that's traveling through a magnetic field.
They're both going to have the same potential difference since the loop's all the way inside the field.
There is no loop here. I know what you're thinking about, and we'll get to that example later. But we just have this entire blob is inside the magnetic field, and all the positive charges have moved to the bottom, and all the negative charges have moved to the top. So which side has the higher potential difference? Which side has the lower potential difference?
I don't think either side has the higher potential difference. I think it's the same.
Well, how would it have the same potential difference across the whole thing? We just said that it generates a potential difference. How do we relate potential difference to electric field?
Electric field is the potential difference over distance.
Mm-hmm. So we have that integral we talked about, right? Where we have, if we could calculate the potential difference by taking the negative integral of the electric field over a distance, dl. Or the opposite way, we can go from electric field, from here. Let me actually pull up the formula sheet from last week because it'll make things easier. (122) course materials, formula sheets, electricity. So we have the potential difference is equal to the negative integral of E dot dl, or we can have the electric field is equal to the negative change in potential. Right? It's just opposites. So clearly there's some electric field here, right? We agree on that?
Right.
Yes.
So if there's an electric field, there has to be some change in potential. It can't be the same potential difference throughout the whole thing. So which side has the higher potential? What side has the lower potential?
I'm guessing maybe the positive has the higher?
Yep, exactly. And then the negative has the lower. something you guys might remember from last week, and it's useful to sort of know this. Electric fields always travel from high potential to low potential. So whichever direction the potential is decreasing, that is the direction of the electric field. So if we have a charge in here, like a separate charge that isn't what's the wording? I'm trying to think. So if we have this potential difference, this electric field, then any charges that are inside our blob are going to end up being pushed in a certain direction, right?
Mm-hmm.
So what exactly is an EMF?
An induced potential difference.
An induced potential difference. So how can we use that to understand, like, how is that related to, like, a current or a voltage or a magnetic field or anything else?
Let's see. Voltage is equal. Well, the voltage is over current portion of the voltage is equal to the current times the resistance if it's in a wire.
Mm-hmm. And so how can we relate either of those to EMF?
Does this blob have a velocity?
Yeah, it just has an arbitrary velocity v.
Okay.
It's all like we're just hand waving right now.
Actually, I have one question. What if there is no resistance?
So real talk, nothing in the world actually truly has zero resistance, because if it would, we'd have infinite current.
Which is basically ideal.
Yeah. So short answer is it is not realistic, and because of that, you won't actually see any problems where something has zero resistance.
Okay.
So you'll see these wires in your circuit problems that have like zero. The wires themselves have zero resistance, and it's just the resistors, and that's just assuming ideal conditions. You won't see any examples of like a loop with zero resistance traveling through the magnetic field, because then the current would be infinite.
All right.
So how is EMF related to voltage?
I believe the voltage is equal as she said is equal to I times R. So the current times the resistance.
Mm-hmm.
The E net is also the same thing. E net also equals the current times the resistance.
So you're saying the EMF is the voltage?
I believe so.
Yeah, it is. That's pretty much it. Honestly, this is one of the things where I don't really understand why this isn't just grouped in with Faraday's law and Lenz's law, because it sort of feels like there's not really much material for motional EMF. It's really just the concept that something traveling through magnetic field, charges are going to be pushed certain ways, and then
I think he did it just so that way he has a lot of quizzes.
Yeah, I guess it's a convenient way to fit in one more class period, because then you'd have like an extra class period where you're not really doing much. But honestly, from this point, it's all about just doing practice problems and understanding the material. So, you guys have any questions so far?
Well, just from the discussion yesterday, it was a problem similar to this where they asked for the maximum current in the loop. And I couldn't really solve it because I didn't know the resistance.
Do you want to look at that problem once we get through these problems, honestly, we'll probably get through these in about 20, 25 minutes. So we'll have
Oh,
about another 15 minutes at the end if we want to look at other stuff.
oh, wait. Never mind. There was a resistance. I just wasn't paying attention.
Yeah.
Problem.
We can
Yeah.
still go
Never,
ahead.
never mind.
We can still take a look at it if you want afterwards. But if you don't have any questions specifically about this, let's just hop into some practice problems. So, first problem, we're going to have a square slab of uncharged metal, side length 5 centimeters, and velocity negative 5 meters per second in the z direction. So we're going to say downward. Actually, you know what? I'm dumb when I wrote this problem. We're going to change these. It's not z direction. We're going to have negative y direction and the positive z direction out of the page. I'm dumb. So we're going to have a uncharged metal slab, side length 5 centimeters, velocity negative 5 meters per second in the y direction, so it's traveling downward. It's going to enter a uniform magnetic field of 300 milliteslas in the positive z direction out of the page. So let's go ahead and visualize this. We have our magnetic field area. B is out of the page. And we have our... Yep, out of the page. And then we have our uncharged metal slab that's going to be able to travel around velocity v downward. So the first thing I want to know is what's going to be the potential difference across the slab as we are inside our magnetic field. And then which side of the slab is going to become positively charged and which side is going to be negatively charged. Take 3 minutes and we'll talk about it.
It should be to the right. No, left. The positive charges will go to the left.
Mm-hmm. So you're going to say the positive charge is going to go to the left.
What's the conversions from for the magnetic field from micro Tesla to Tesla?
So you just multiply it by 10 to the negative 6.
But
Okay,
this isn't micro.
Oh, sorry. What does the M mean in this case?
Milli.
Oh,
Milli. So it's times 10 to negative 3.
Exactly.
Okay, then. I did say the wrong one, so my bad.
So, as you guys said, we have the positive charges are going to end up moving to the left side, which means the negative charges are going to move to the right.
Yep.
So, what is going to be the potential difference across the slab?
It's gonna be like 7.5 volts.
7.5?
I'm getting I'm getting 0.075, and that's not including the negative too, because the velocity is negative.
Oh, yeah, it's 0.075. I
Yep.
forgot to convert the length.
Yep, centimeters to meters. Yep, it's pretty simple. The way we get the potential difference is just the EMF, which is just the velocity times the magnetic field times the length. Now, which length is this? Obviously, for this one, it's a square, so it doesn't matter. But what if we were instead to have... Let's see, is there a way for me to easily do this? I'm going to do this. Now, imagine our block was twice as long, so it's 5 centimeters by 10 centimeters. Which one would we use here for calculating the EMF?
I believe it's the side with the charges.
So we'd use the 10 centimeters.
I believe so.
Any other ideas? Any other reasonings?
Wait, reasonings for what exactly? Sorry.
What was that?
Reasoning for...
It's just which one do you have to use the link for? That's it. I'm thinking the one with the charges. So I could be wrong on that one.
Well...
I feel like I am.
What gives away the fact that you're wrong?
Well, first of all, the dead silent. Second of all, now that I'm looking at back a little bit of the notes, it looks like the length was going with the electric field. So probably it's not the side with the charges, it's the side without the charges.
Yeah, that's what I'm thinking too.
Yep.
Okay then.
Yeah, so we use the side that is essentially perpendicular to the direction of movement. So this side here is the side that's entering that's moving through the magnetic field because the velocity is down. So we use this side here, the 5 centimeters. If we were traveling to the left, we would use the 10 centimeter side. It's whichever side is entering the magnetic field, or as you said, it's the side that has the direction of the generated electric field. It's parallel to the electric field.
Okay, so that's good. All right, that's good to actually keep a note on that one.
Yep. Nice and simple. But thankfully, most of the examples you'll see are going to involve square loops of wire, or you might see like a wire, what's the thing? You might have like a wire that's like on a track that slides along, where like, for example, you have a set wire here, and then you'll have a wire that can like slide along here. Thankfully, those are pretty simple to figure out the length for. It's the part that's actually moving. You guys have any other questions about this one?
Nope, none for me.
All right. In that case, let's go ahead and take a look at a square loop of wire that's going to travel at 5 meters per second to the right. It's going to enter a 2 Tesla magnetic field into the page. So we're going to have our magnetic field. B is into the page. We're going to have our square wire loop traveling 5 meters per second to the right. First thing we want to know is what is going to be the induced EMF and current in the loop as the loop first enters the magnetic field here, second, when it is fully inside the magnetic field, traveling to the right, and third, when it's exiting the magnetic field over here. And also, it appears to be growing as it travels through the magnetic field. Amazing.
Well, that's not supposed to happen.
Yeah, I just suck at drawing stuff. But yeah, take 5 minutes, and then we'll talk about this.
Maybe it's due to thermal expansion from the heat of the current going through. Why it's expanding?
Big brain right there. Thermal expansion.
I don't think it would be that great, but
Yeah.
should consider it.
It's not negligible. I swear. All right. So, we want to be able to understand what the EMF and the current are going to be in the loop as it enters the magnetic field, as it travels through, and as it exits the magnetic field. So, how do we go about doing this? First of all, as it enters the magnetic field, how do we calculate the induced EMF?
Well, E should equal VBL, which is the velocity, the magnetic field, and the length.
Yep, and which length is it?
Well, it's square. It really doesn't matter, but the square of it's the length of the moving.
Exactly. It's the length that is perpendicular entering the magnetic field.
Perpendicular. Okay.
And
Write that note. There we go.
is this EMF going to change based on how much of the loop is inside the magnetic field? Like, what if half the loop is inside, or what if it's only a quarter of the way inside? Is it going to change?
I think it does because depending of how much is in the magnetic field.
So you're saying it does change?
I think it only just the only thing I'm trying to figure, like, I know the velocity doesn't change, and of course the length does not change.
And
But as you're entering the magnetic, I don't think the magnetic field is out because we're trying to put it in the magnetic field. So outside of said magnetic field, it'd be 0. So if it's play inside, I do think it does have some change to it, but I don't think it's like if it's halfway in, shouldn't it be half the magnetic field because it only affects some of the charges as well? That's only my reasoning, but I could be just wrong on that one.
So you are incorrect, but you're not completely out of the ballpark. And you're thinking not about magnetic field, you're thinking about magnetic flux. Do you remember what electric flux is?
Yeah, yeah.
Well, what is it?
Let's see if I can get that note back up, and because I know that should be the next part for class, I believe. Wait, where's that note about the electric flux? Oh, there it is. E times D, E dot dA, which is the charge enclosed over E naught.
So basically what electric flux, it's like the total amount of electric field lines passing through a surface. And in this case, the magnetic flux, which is what you're thinking about, would be the total amount of magnetic field lines passing through a surface, or in this case, an area, the area within the the circuit loop.
Okay, so
So as we're halfway through, obviously there's going to be half as much flux through as when we're completely inside.
okay, but in this case, since we just want the magnetic field, it would be the same. Okay, then.
Yeah. So nothing's changing. So that means it doesn't matter how much we're inside the loop, it's always going to be the same induced EMF, whether we're just entering or if we're 99% of the way in. So,
Okay.
and then how do we get the current?
How we get the current? It would be, well, how we by formula wise, we could use the E net is equal to I times R, the
Mm-hmm.
current times the resistance, and E net is the same as it's velocity times the magnetic field times the length.
Yep. Essentially, you just take your EMF and you divide it by the resistance. How do we find the direction of the current?
Uh, is this where we need to actually draw the graph for that? I don't know on that one.
What graph are you talking about?
uh, uh, what is that? What is the name of that? Just one. Induce current as a function of time. That would when we do the discussion. It's the second. It's when we go over the discussion. I can show you
I
which
think
question. It is.
I think I know what you're talking about. Yeah. But so that's not really going to help because we need to understand what direction the current is in order to draw that graph anyway.
So let's see. This current. Well, the only other thing I can think of is right hand rule. Now
Mm-hmm.
my question is how do I?
Absolutely. There's going to be a right hand rule you can use to find this.
So let's see. Huh. Now the question is which right hand rule? Loop of wire, and it carries a current. So it should. So I think we have to use the right hand rule of direction of the magnetic field inside a current carrying loop.
So take me through your process.
It's the one where you point your thumb and you point your thumb of the curve of the loop. Oh wait a second, we don't even know what the direction of the loop is. Never mind. Wait, no, not the direction current for part of that loop. Uh, I'm trying to think. It's the very last one. That's what I was talking about. But we don't know the actual direction of the loop current.
Yep. So this right hand rule you're thinking about is going to be for tomorrow's material with Lenz's law.
Dang nabbit. Okay.
But there's a simple way. There's a much simpler right hand rule that we've already used in this session that you can use to find the direction of the current.
So it's the second one. I believe it's because you point because it's the. Oh well, technically it's the first one. Point at the direction of velocity.
Exactly.
So, okay, it's the first one, not the second one. It's the first one.
Mm-hmm.
Oh wait, the first one is basically similar to the second one.
Yeah.
So so the current is the exact same direction as the velocity, right?
So what do you mean by that?
Well, isn't let's see, point fingers in the direction of the velocity.
So that's to the right.
And let's see, rotate your palm and curl your fingers in the direction of B, so into the page.
Mm-hmm.
So the force of the magnetic field would be up, which that would lead the charges on the top be positive and the charges on the bottom be negative.
So the positive charges move up, the negative charges move down. And what about over here on this side? Is there any force acting over there?
No, so that shouldn't be messing with that.
Yep. There's nothing. So the only force acting on the loop here is acting on the right side. It's forcing the positive charges up and the negative charges down. So what direction?
Okay.
So what direction is the current in the loop going to travel?
To the right? Wait.
Clockwise or counterclockwise?
Okay, I'm being dumb. Yeah, okay, positive charges up. Into the fields into the page. I think it's clockwise?
Clockwise. So the positive charge. So if the current's clockwise, you're saying the positive charges are going to move against it here because they're going to move upward.
Oh no, they have to go with it. So other way around.
Yep.
Counterclockwise. Okay.
Counterclockwise current.
All right. Okay. That's going to be something I'm going to keep my.
Yep.
Gotta keep my mind on.
So the positive charges are forced upward in this section of the loop, and all the charges in the entire loop are essentially going to move like a conga line. And if some of them are being forced in one direction, all of the charges in the entire loop are going to move in that direction. So it's all going to be forced into a counterclockwise current direction. What about B when we are fully inside the magnetic field as it's traveling through?
Let's see. E should not change because that should be constant throughout. And I believe the current would be 0.
So then how would EMF be 0? How would EMF be the same, but the current be 0?
Right, maybe not current itself is 0. The induced current would be 0.
Mm-hmm.
Okay, like that, because that's the proper term on that.
So what do you mean by the induced EMF? So what do you mean by the EMF being the same throughout the whole thing?
Even as it moves, nothing is changing. The velocity is not changing, the magnet field itself is not changing, and the length itself is not changing.
Mm-hmm.
So it does not change whatsoever throughout the entire thing.
What's different about scenario B versus scenario A?
One's completely inside, the other one's only halfway inside. The only thing that would be different is the magnetic flux.
So, but this left side, while it wasn't inside the magnetic field before, it is inside the magnetic field now. So what direction is the EMF on the right side of the loop? It's going to be forcing positive charges upward, right? Same thing as before. What direction is the EMF going to force positive charges on the left side of the loop?
Oh, left side of the loop? None.
Well,
it will. Okay.
The whole loop is traveling with the same velocity, right?
Yeah. So. Well, all the positive charges would be on top, and all the negative charges would be on the bottom.
So the positive charges are going to be forced upward on the left
Yes.
side? So basically the EMFs here are counteracting each other. Right? The induced EMF on the right side and the left side are opposite of one another. They're going to counteract each other, and the net EMF is going to be 0.
Oh. Oh, okay then. I must have been. I thought maybe I've got some things mixed up. All right.
I mean, you had the right idea. You said that, oh, the current is going to be 0, but the EMF is going to be the same. And I was like,
Actually, that wouldn't make sense at all.
yeah.
Yeah.
You were technically like 70% of the way there.
Yeah.
You
I
had
understand.
you had the right idea that yeah, for each individual for the right side of our loop here, the EMF is indeed the same. But now we have to take into account the left side because the left side is going to counteract it, so the net EMF is going to be 0, and therefore the current is going to be 0. So 0 current. Now, what about scenario 3 when we are exiting the magnetic field?
Well, now that should be it should be around the same EMF as the first one, but I believe in the negative. Like, since it's just the left side this time instead of the right.
Uh-huh. So we have only the left side with the EMF acting upward.
Yeah, and if it is counterclockwise throughout the whole loop, then yeah, it would be in the negative. So the EMF would, assuming that's the same halfway out, it should be the EMF, the same EMF as it enters halfway through,
Yep.
just negative.
Yep, exactly. So it's just going to be the exact same EMF and therefore same magnitude of current, but it's going to be traveling clockwise instead of counterclockwise. Because the force is acting upward on the left side instead of upward on the right side. You guys have any questions?
Nope.
That's
Nope.
honestly that's about it for I mean, I'm sure as you saw, you basically had the exact same problem on your discussion, and you had to like draw a graph for the induced EMF over time, or the now you've sketched a plot for the induced current as a function of x over the full range of motion. And did he also have you guys do the for the wire loop near the? Okay,
Well,
that's interesting.
I did not get to that point. Once I got to 3C, it was like already 6 and it was thunderstorming outside. I was just like, I'd rather not take the chance of electric going out.
Oh my god, that thunderstorm last night was crazy. I made the horrible decision to drive to the gym at 5:50 p.m. and the second I pulled into the parking lot, it was just torrential biblical downpour for 25 minutes straight. I sat in my car for like 25 minutes waiting for it to die down slightly, and eventually just sucked it up and ran inside. So do you guys want to go over question 4 here? Because we still got about 10 minutes.
I'm okay with that, yeah.
Alright, so we have a rectangular loop. Width is 10 centimeters, length is 30 centimeters. It's traveling to the right at a constant speed of 2 meters per second. The loop has a resistance of 5 ohms. The loop is a distance of 20 centimeters from a very long wire, which carries an upward current. I naught is equal to 4 amps. So what we want to know is, what is the induced EMF in each of the wire segments of the loop? Determine the magnitude in microvolts and which end will be positive / negative.
Oh, in each segment. Oh, God.
So why does it specifically say in each segment of the wire loop?
What was that one? That's why I'm just double checking.
So what are the three things we need for an induced EMF?
Velocity, magnetic field, and the length. Or
Yep.
L, in this case, L could be anything with the length.
Yep. So
Like,
we have our lengths, which are going to be W and L potentially. We have the velocity. Do we have a magnetic field here?
no.
Why
Well,
not?
well, it doesn't say it. We don't know. Well, okay. Maybe the better thing for me to say, I bet you there is a magnetic field, but we don't know what it is.
So, what here could potentially be generating a magnetic field?
The current.
Yeah, the current in this long wire. What's the magnetic field due to a very long wire?
Oh, okay. Where's that right hand rule again? If it's that way, is it out of the page? Hang on. Can't use that one. Yeah, shouldn't it be out of the page in this case?
Would it be? I'm messing with you, of course.
Okay, yeah, I was about to say, sorry, there's no other right-hand rule, and the current's point up. So at this point, it has to be going out of the page.
Yep. Thumb points up, and your fingers curl around. They come out of the page on the left side, and they'll go into the page on the right side, obviously. And then it just like loops around.
And we just don't know the number of the magnetic field.
Yeah, how do we get the magnitude of the magnetic field?
Oh, now we gotta use the U naught times the current over 2 pi r, right?
Yep.
And R being either L or W, depending on which segment.
Hold up. What?
Just trying to figure out which the R is at that point.
The R, mu naught I over 2 pi r. This R is just the distance from I naught.
Oh, okay. The distance from I naught. All right, I keep mixing that up. So the distance from that would be D. Okay then. So R will be D.
It'd be D for this side of the loop.
Oh yeah, for that segment. It's so depending on the other segments of for D. Got it.
Exactly. So, what is the induced EMF in each of the wire segments of the loop? So for the first one here, from B to C, what would be the induced EMF? So we'll call it EBC.
So
EMF is a velocity.
Yep.
Times the magnetic field, which we'll get to in a second, times the length. What is the length here?
For this one, it'll be the width, so it'll be 0.1 meters.
Yep, it's W. I'm leaving it as variables because it's easier.
Okay. Maybe I should.
And then we have to multiply by the magnetic field, which is mu naught I naught over 2 pi, and then the distance from I naught, which is D. And then which side would be positive or negative, positive / negative.
See. It's going to the right. Wait, what do you mean by which?
Yeah,
which side be?
Which end is going to be positive? Which end is going to be negative?
Oh, C. Oh, hang on. I think I almost got it wrong. Velocity going to the right. Out of the page. Okay. C should be negative, D and B should be positive.
Yep, exactly. So negative,
Okay, fan, stop blowing this sheet
positive.
around.
It's just a big fan of your work. I'll show myself the way out.
Yeah, please.
So what about segment AB?
All right, so that should be the velocity times the length times u naught I naught over 2 pi. Now what is this D gonna be? It's still gonna be D, but it's not. That's gonna be the same number because it's a longer distance. Actually, is it a longer distance?
The distance is changing. I mean, the whole
Okay,
thing,
yeah.
the loop isn't a constant. The magnetic field isn't constant along this part of the loop. But does that even matter?
No.
Why wouldn't it matter?
To be honest, I'm not sure.
Well,
So,
let's think of it this way. What direction is our velocity?
it's that type of thing. Got it. Our directional velocity is to the right.
Mm-hmm.
And I believe that, I think that causes a parallel to something, which makes it 0.
Yep, exactly.
What is it parallel to? That's my question. I know it's a parallel at this point, but
So
parallel to
It's
what?
parallel to the other length. Parallel to the length of of CD. You'll have the same current, but in the opposite direction.
mm-hmm. I mean, not quite. It's more of, I mean, because both AB and CD are 0, because the side length here is parallel to the velocity. So so like essentially there's only a non-negligible EMF on the side lengths here that are perpendicular to the velocity.
Okay.
That makes sense.
It's sort of like, actually that's a bad example. I'm not going to say it, but yeah, basically parallel to the velocity, no EMF. Perpendicular, there will be an EMF. And this is
Okay.
one of the reasons why I don't quite like looking at EMF before Faraday's law, because then we could like actually sort of understand it here. But regardless, and then what about side length AD?
Well, AD, that should be a negative form of it too. VW U naught I naught over 2 pi. And again, this time the distance does matter in this case.
Mm-hmm. What's the distance?
I've
Well, it's D. It's D to get to this end of the loop, and then it's another L to get out here.
Oh, so D plus L.
Yep,
Okay then.
D plus L. And then, so which end is going to be positive? Which end is going to be negative?
D should be negative, A should be positive.
Exactly. So then, how would we actually find the current in the loop?
Don't we have everything to find that current?
I mean, we have EMFs for 2 side lengths, which are traveling in the opposite direction of each other.
Oh yeah, the current equals to the EMF over R.
Exactly. So we just we essentially take the difference of these two EMFs because they're opposite to one another, and we divide it by the resistance, which is 5 ohms. So what direction is our current going to travel in?
Oh wait, no, I'm doing that wrong. The positive is going down, so in order to go the same way, it has to be clockwise.
Clockwise. Yep. So for the right side here, we have the force is going to essentially pull the positive charges down, so it's going to create a clockwise current. And on the opposite side, on side AD, it's going to pull them down, so it's going to create a counterclockwise current.
Yeah.
So, but the side length BC is closer to I naught, so it's going to be a stronger magnetic field and therefore a stronger EMF. So
so it will be in a positive. It would still be clockwise, and then it will be positive.
Yep.
Yeah.
And then, so how would we find the external force necessary on the loop to keep it moving to the right at the constant speed of 2 meters per second?
Oh God. Okay, that's the. Where's that one? Oh, that's the sheet. Oh no, that won't even work either because that. Wait. I'm not entirely sure. Will it have to be the formula for Unit 18 on the formula sheet? Let's see, I'm trying to figure out the external forces, but that's the only one that could...
Well, this would be the forces acting... between two wires. Mm-hmm.
This is just the one. So... Wait a minute. We know the current, and I believe we know the length, when did the length... I was thinking maybe Unit 17 for the force, or maybe...
I think Unit 17 looks mighty nice right now.
Yeah. So we know the current, or at least we should, the direction of the current.
Mm-hmm.
And I believe we know the direction of the length across the magnetic field.
Yeah.
So that's the formula you'll have to use to figure out the external forces.
So how much force is acting on the right side of the loop?
Let's see. Let's see, magnetic fields outside the page.
And the current is
Clockwise.
So for the right side, the current is downward.
Okay, hang on. Current's going down. Outside the page. Force to the left.
Mm-hmm. The magnetic force acting on it is to the left.
Yes.
And what about the bottom segment?
Okay. From that part, the current will be going to the right. And then it's still out of the page. Up?
Yep, upward. And what about top segment? Well, the current's traveling opposite, so it's going to be downward.
Yeah, and it would also cancel each other out.
Exactly. And then what about the left segment?
It should be to the left, I believe. Hang on.
Current's upward.
Current's upward. Out of the page. Oh, no, still to the right.
Yep, so the force acting on the right segment is pushing it away to the left, and on the left segment it's pulling it into the right. but the magnetic field isn't the same, right? It gets weak.
Right.
It gets weaker as you go further out. So
Mhm.
the force acting on the right side from the magnetic field is going to be stronger. So this loop is going to naturally want to be pushed away. So we need to pull it with a force that is equal to the difference between the forces acting in order to pull our loop along at a constant speed.
Huh.
And
Alright.
we could calculate it, but I don't feel like it, and we're pretty much out of time.
Yeah.
But it's essentially you calculate the force for the two segments and take the difference. And you calculate it with IL cross B.
Okay then.
So, yep, that's about it. You guys have any last questions?
Nope, I don't.
Nope, none for me either.
All right. Well, in that case, let's go ahead and wrap up the session here. Thanks, guys, for coming. Good luck studying for your quiz tomorrow. And honestly, this material isn't too much to worry about. It's really just understanding right-hand rules and VBL, and that's pretty much it. So, thanks, guys, for coming. And I got to go prep for my 121
Alright.
session. So,
Thanks for having us.
yep. See ya.
Thank you. See ya.